Okay, we are going to look at a system of equations. A system of equations is just two or more equations that have been paired together as one graph. Okay, so we have two equations, and usually they are combined with a curly brace in front. Just one. There's not two, it's just one to let us know that these two equations belong together. And they are making, the two equations together are making one new function, one new graph. Not a function, but a new graph. Okay. So these two equations are a system. And the question is asking, is the ordered pair a solution of the given system? What that means is, does this ordered pair, this particular x and y combo, does it work for both equations? So what we do to actually figure out if it does is we plug it in. Okay, so plug in x as -4 and y as 2 into the first equation and see if it makes sense. Okay, so this would be -8 plus 2, and the question is that -6? It sure is. Okay, so we get -6 equals -6, which is a true statement. Then we know that this ordered pair is a solution to the first equation. But if it's going to be a solution for the system, it has to be a solution for both. So let's go ahead and plug in -4 and 2 into the second equation as well. Okay, so is -4, 2 a solution to this equation? -4 plus 6 equals 2, and that again is the truth. Okay, it works out. So we get 2 equals 2. So this ordered pair is a solution to both equations. And when that happens, we say that this ordered pair is a solution to the entire system. So what's the question? Is it a solution to the system? Yes, it sure is. If -4, 2 was a solution to the first equation and not the second, then no, it would not be. So it has to be a solution to both to be a solution for the system. Some different things can happen when we're looking for solutions to the system. In this first case, what's happening is you have two lines and they're being graphed. Okay, so this first one we have two equations being graphed and they intersect in one point. This point where they intersect is the solution to the system. Okay, so that's all we're looking for really. If we have a case where our two lines, we graph them, they're parallel, they never intersect one another, then there's going to be no solution because there's no intersection, there's no point in common between the two lines. So this would be no solution for parallel lines. Okay, we say the two systems are inconsistent. That means they don't ever cross, and they are independent equations. And in this third case, that's where we graph one line and then we graph the other, and when we graph the second one, it ends up being right on top of the first. So the two lines in essence are the same line. We say we have a consistent system. That means it does have a solution, but the equations are dependent, which means they're the exact same line. So in this case, the line, the entire line, is the solution because every point on that line will work for both equations. And then, of course, in the first case, we have a consistent system. That means we have a solution. We have independent equations, which means they are different equations. We can solve systems of equations in a few different ways. We're actually going to learn 3 ways: graphing, substitution, and elimination. The first way is graphing. So we have a system of equations, and remember they have their curly brace right here. Then we can graph each one of these lines, and we can see where do they intersect. So when we graph the two lines, okay, this is the first line, this is the second line, we can see that they actually intersect right here at this point, -3, 1. So if you can graph it and see where they intersect, and a lot of times you can do that on your graphing calculator. Your graphing calculator will actually calculate the intersection for you. If you press calc and calc is second trace. So second trace. And then go to intersect, which I believe is maybe number 5. Intersect. And then it's going to ask you for a y1 and a y2, and then it's going to ask you if you want it to guess. So you have to press enter, I think, 3 times. And it will calculate that point for you. And you can also just do it by graphing by hand. But if you can find out where the 2 lines intersect, that will be your solution. The second way, and probably a more precise way to do it, sometimes graphing can be a little ambiguous, is by substitution. Okay, so substitution means that we have our 2 equations. This works well when we have one equation solved for one of the 2 variables. In this case, the second equation is solved for x already. It makes it really easy to then just in the first equation, instead of having x, we're going to plug in 2 minus y in place of x, okay? Because we know that x equals 2 minus y. So we can plug that in and then solve. So we're going to write the first equation, but instead of x, we're going to write 2 minus y, and then copy down the rest of the first equation, and we can solve for y fairly easily. So we have 10 minus 5y minus 3y equals negative 6 after we distribute. Now we're going to add like terms. 10 minus 8y equals negative 6. We'll subtract 10 from both sides. Negative 8y equals negative 16, and divide by negative 8 on both sides to get 2. Okay, but this is not the end. Okay, so this is something you have to really try to remember. We have one of the 2 variables solved, but we need to get the other one. So we're going to come back up to the top, pick either one of the 2 equations, and plug in 2 for y. I'm going to use the second equation because I think that will be easier. We'll plug in 2 for y. 2 minus 2 is 0. Now we are finished. Okay, we have our x and our y, or if you want to write it as an ordered pair, 0, 2 is the solution to both of these equations. The third way we could solve a system is by elimination. And the idea of elimination is to add the 2 equations together in a clever way so that we can cancel out one of the 2 variables. Okay, so first of all, we're going to decide which variable we'd like to cancel out. And I'm going to say, let's go ahead and try to cancel out the y's. But what happens if we add the 2 equations right now? We will add like terms. 4x plus 2x is 6x, and y plus negative 3y is negative 2y, and 5 plus 13 is 18. Okay, so if we add the 2 equations, notice that everything is lined up before we add them. Okay, that's one thing you have to make sure, that you have your x's and y's on the same side of the equal sign and your constant terms on the other before you add. But when we add, we end up with still x's and y's in the answer. So that didn't help us at all. We want to add in a clever way so we can eliminate y's. Okay, so what we're going to do is multiply one or both of the equations by something to begin with. That way we can eliminate something. So I'm going to copy down the equations. 4x plus y equals 5, and 2x minus 3y equals 13. And let's go ahead and multiply the top equation by 3. And we're going to leave the bottom equation alone. And you'll see what will happen. 12x plus 3y equals 15. And 2x minus 3y equals 13. So now that I've chosen to multiply the top equation by 3, notice I distributed the 3 everywhere, okay, to every single term in the equation. Then we're going to add, and what will happen is that the 3y and the negative 3y will cancel each other out, and the y's will be eliminated. So we'll have 14x right here, 0y right here, which is nothing, and then 15 plus 13 is 28. Okay, so we have the equation 14x equals 28, which is very convenient for us. There's only x's. We can solve by dividing both sides by 14, so we know that x equals 2. And see how fast elimination can be when you choose very carefully how to multiply your equations. So you're going to have to practice a little bit getting used to looking for the right numbers to multiply each equation so that you will have something, either the x's or the y's, eliminated. Now, we're halfway there. We have our x, but we're not completely there. We need to then go plug in our x into the top, either one of the two equations, to find y. I'm going to plug it into the first equation. 4 times 2 plus y equals 5. So we have 8 plus y equals 5. Subtract 8 from both sides. Y equals -3. So now we're done. Or we can write our answer as an ordered pair. Great. Okay, we've talked about the 3 different ways to solve equations by graphing, substitution, and elimination. Now I'm going to talk about 3 different things you could run into while you're trying to solve equations. And I'm going to do these 3 examples using elimination because that's the method that I find easiest. You may like substitution or graphing better, and that's great. You please use whatever you feel comfortable with. Just remember, for graphing, you want to get an exact answer, so don't settle for a rounded answer. And if you're going to use substitution, you need to solve for one of the 2 variables in one of the 2 equations first. Okay, so what if we have fractional coefficients? For example, we have this second equation, 1/2 x equals 1/4 y equals 1/2. In this case, I would go ahead and recommend multiplying by the least common denominator first. That way you can end up with both equations having no fractions, and it'll be a little bit easier. So I'm going to copy down the first equation because it doesn't have any fractions already. -2x plus 5y equals 22. And I'm going to multiply the second equation by 4 and distribute that 4. That way I can get rid of these coefficients that are fractional. So if we multiply this by 4 over 1, what will happen? The 4 will cancel out with the 2. We'll have 2 in the numerator, 1 in the denominator. Okay, and if we multiply by 4 over 1 right here, the 4's will cancel. We'll just have 1. If we multiply by 4 over 1 right here, 4 and 2 will cancel. We'll have 2 in the numerator and 1 in the denominator. So that's pretty messy. Let me copy it down over here. 2x plus 1y equals 2. Okay? So I just multiplied by the least common denominator to get rid of my denominators and have just an equation without any fractional exponents. Now we want to decide what should we multiply by so that we can add these 2 equations and cancel out things. We don't need to multiply by anything actually, because if we add them right now, the x's will cancel out already. So we'll get 6y equals 24, and then divide both sides by 6. Y equals 4. Alright, so we have one of the 2 variables. We're going to bring this y back up to the top, choose either one of the 2 equations, or if you would prefer, you can choose this new equation with no fractional exponents. Either way is great. I'm going to go ahead and try that one. So in place of y, I'm going to put 4 into this equation right here with no fractional exponents, and go ahead and subtract 4 from both sides. 2x equals -2, so x will equal -1. Now I have my 2 answers. Okay, you can write it as an ordered pair. Done. Great. Okay, I also wanted to show you, secondly, an example of solving a system of dependent equations. So I don't know if you remember from earlier, but dependent equations are when the 2 equations are really the same equation. So when you go to graph it, you're going to get one line on top of the other line. And a lot of times when you start, you don't know that they're dependent. In this case, we already know they're dependent, but let me show you what happens. So if you're trying to solve this by elimination, copy down the first equation and the second, and we're going to decide what we need to multiply by. In this case, let's try to cancel out the x's. Sounds good. Okay, so if we're going to cancel out the x's, then we need to multiply this first equation by 4, and we'll leave the second equation alone. So the first equation becomes 8x plus 4y equals 24. And the second equation will stay at negative 8x minus 4y equals negative 24. So what happens when we add, eliminate, 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 we get 0 equals 0, which is a true statement, okay? So that's the key word. This is true. It's true, but it's not helpful. Okay, so when you end up with a statement that's true, that doesn't have any variables in it, you know you have dependent equations, okay? Dependent equations means the lines are parallel. Not parallel, sorry. The lines are the same line, one line on top of the other. So the answer is just that one line. Okay, that line itself is the answer. What if you had written the second equation? It doesn't matter because they're the same line. So the entire line is a solution for both equations, which means the entire line is the solution of the system. And what happens when you're solving a system of inconsistent equations? Which means that the two equations are parallel, they never intersect, and so there's no solution, okay? Most of the time you won't know going into it that the equations don't ever intersect. And so you won't know there's no solution until you find out. And so what happens in the process that tells you there's no solution? So let me copy down these. We're going to solve it by elimination again. What do we need to multiply by to cancel out the y's in this case? We have negative 3y, negative 6y. So if we multiply this first equation by 2 and the second equation by negative 1, we will end up with equations that will have things we can cancel out. So 8x minus 6y equals 16, and in this case negative 8x plus 6y equals negative 14. Okay, so our x's will cancel and our y's, and we'll get 0 equals 2. Alright, so here we ended up with an equation that has no variables in it, just like in the previous example, but this time it's false, because 0 does not actually equal 2. So when you end up with something that is false, that means that you have no solution, because no matter what happens, there's no way that 0 will ever equal 2. So you have inconsistent system, inconsistent equations. That means they're parallel, they never